When light is reflected by the surfaces of a thin transparent film, such as an oil slick or a soap bubble, thin film interference occurs. This is the result of two things.
When light waves pass from one medium to another, the interaction at the reflective interface can affect the phase of the light wave. Secondly, the thickness of the thin film itself determines the path length that light reflected from the second interface must follow. This path length affects its phase relationship to the original incident light beam.
This disturbance of light by thin film has many practical applications. For instance, the glazing on buildings or binoculars, or the retrieval of information from a laser disc.
Let's begin our discussion of thin film interference with simple reflection. This is a polished steel mirror. If I look into the steel mirror, I can see my reflection. Because it's made of a single material, it has a single light interface between air and steel. The light we see is reflected by that interface.
Now, if we look into a thick plate glass mirror, what happens? We still get a reflection. It's nice and clear because the silver coating on the back of the mirror is a very good reflector. But look a little closer at the reflection of my hand. Can you see another reflection? Here on the surface of the glass, you can just make it out. This is, in fact, a reflection at the mirror's first interface, between air and glass, while the sharper reflection is at the second interface, between the glass and silver.
Here is a third phenomenon. We can coat the steel mirror with a thin film of soap. Look at what's happening on the surface of the steel. You can see swirling rainbow-colored patterns. That's a result of the light reflected at the first interface interfering with the light reflected at the second interface of the soap film. The colored pattern is a result of thin film interference.
We've just seen that light can be reflected in a number of ways, depending on the types of media it encounters. What is actually happening to these light waves as they move through different substances?
Let's look at the steel mirror first. At the interface between two media of different optical densities, in this case air and steel, the reflected light wave undergoes a 1/2 wavelength or 180-degree phase shift. This occurs whenever light travels from an optically less dense medium into one which is optically more dense. It's important to note that this does not occur when light passes from a more dense medium to a less dense medium.
Now, if we look at the plate glass mirror reflection, what do we see? A small amount of light is reflected from the first interface. It incurs a phase change of 180 degrees as it is being reflected. Most of the light is being reflected by the second interface, and because glass is optically less dense than silver, the light reflected from the second interface incurs a phase shift of 180 degrees.
This brings us to our third case, the soap film on the mirror. The light here is acting much the same as it did when reflected by the plate glass mirror. Reflections from the first interface, air and soap, experience a 1/2 wavelength phase change, and reflections from the second interface also experience a 1/2 wavelength of phase change. However, the distance light travels within the thin film of soap also affects its phase, even though it's very thin, a couple microns at best. This is how it works. Since light waves being reflected from the second interface of the film must travel further to be re-emitted than waves which are reflected from the first interface, the two light beams may no longer have the same phase relationship. As these two reflected waves interact, they either reinforce or cancel each other. Because the soap film is not uniform, the path lengths of the refracted light are different, and therefore different colors or wavelengths of light are affected. If I move the mirror, you'll notice that the colors appear and disappear, depending on the angle at which the film is viewed. Changing the incident light angle or the viewing angle alters the path of light in the medium and reinforces different colors. The constructive or destructive interference of light due to thin film interference depends on two things: the phase change induced by the optical interfaces it encounters, and the path length, or the distance that light travels within the medium before being re-emitted.
When the path length traveled by light in a thin film medium is equal to one wavelength or any whole number multiple of its wavelength, both reflections are in phase and constructive interference occurs. This results in brighter, more intense reflection of light in the portion of the spectrum in which that wavelength occurs. When the path length traveled by light in a thin film medium is equal to an odd number multiple of half its wavelength, such as 3/2 or 5/2 or 7/2, the reflections will be out of phase with each other and destructive interference will occur. This results in no light being reflected.
Let's see if we can demonstrate this. This is a plano convex lens. Look what happens when I set it on this flat glass plate.
See the dark and bright rings? Those are called Newton's rings, and they are progressive patterns of constructive and destructive interference. The air between the convex lens and the glass plate acts like a thin film. As the thickness of the film increases, the path the light travels changes from half wavelength multiples to odd number multiples, producing first constructive and then destructive interference.
The same thing occurs with these two plates of glass when they're oriented to produce a thin wedge of air between them. The change in the thickness of the air wedge causes the path length of the reflected light from the bottom plate to vary. It gets progressively longer. This is what causes the interference pattern we see.
Interference doesn't only occur when light is reflected by a thin film. The same process also occurs when light is transmitted through a thin film. Most industrial glazings which provide some sort of screening capability work on the thin film interference principle. Let's consider a thin film suspended in air.
In this instance, some of the incident light is transmitted directly through the medium. It does not incur any phase change at all. But a portion of the incident light is reflected within the film and then emitted after the second reflection. Because both reflections occur from more dense to less dense media, from thin film to air in both cases, light reflected at the second interface will not incur a phase change due to reflection.
Of course, if the path length traveled by the light in the thin film is equal to its wavelength or any whole number multiple of its wavelength, light traveling this second path will be emitted in the same phase as the light which traveled along the first path. The net result is constructive interference.
However, if the path length traveled by the light beam in the film is equal to 1/2 its wavelength, or any odd number multiple of 1/2 its wavelength, again, such as 3/2, 5/2, or 7/2, this second beam of light will be emitted 180 degrees out of phase with the incident light which traveled along the first path. This will result in destructive interference, and that particular frequency of light will be canceled out.
The path length difference can be regulated by changing the thickness of the thin film. In this way, a particular wavelength can be screened out.
Let's look at a compact disc again. If we could take it apart, this is what we would have. A thin film of plastic covering a thin sheet of aluminum.
If you place the aluminum disc under a microscope, you would see that it is dimpled with regular depressions throughout its surface. What causes the rainbow-colored patterns we see on a compact disc?